a course like this, because this course is I would say a highly customized course for the first year batch, because we try to give an overview of the entire electronics and communication engineering, and the focus is more on semiconductor technology, the electronics that depends on semiconductor technology, and later on communication technologies and RF and microwave technologies. So there is no single book per se for semiconductor part, though I would suggest you to maybe read Streetman and Banerjee, although that is quite an extensive book, so all that will not be important here. Uh, but some excerpts from that book might be helpful for you, actually. Even I'm taking some figures from there. I'm taking figures from multiple places, but Streetman is a decent book on semiconductor physics, but that's an advanced book, and maybe you would need to refer to that book in your second year course, ECN 242. So I would suggest that I would rather say that using a book is not, or referring a book is not what is required in this course, because there is no one standard book, one particular book for this course. So what you can do is you can listen to the lectures carefully, and if you do that and you make notes from the lectures, that should be sufficient for the exams and even for the entire understanding of these things. Okay. So let's maybe begin with our yeah. Somebody has any concern? Let's maybe yeah. If there is any question, please ask. Otherwise, we can begin the discussion.
Sir, what will be the amount of money that you will provide to us for the course project?
Yeah. So that as I told you that the amount of money given to each group last year, 2 years back, was 1,500 per group. Okay, and but we only had around 20 groups, and since you guys are doing individually, okay, so if a lot of you, many of you choose to buy hardware, then this money might be limited. But if, for example, you are only around 20 or 30 of you are only choosing to build things, then we can this money up to 1,500 rupees can be given at least. Actually, the department budget is a bit constrained, so that's why, especially during COVID times, things are. Yeah, so you can assume up to 1,000 or 1,200 at least. You can assume that kind of money. Okay. So let's maybe not delay further. This is what we. I hope all of you see slides on your screen, and this is what we have been discussing. We discussed in the last class, and this is essentially a PN junction. It is an extremely important, I would say, electronic device, uh, and this is PN junction in equilibrium. And I hope most of you understand what is equilibrium. Equilibrium is when we do not have any voltage applied across the junction, and each kind of carrier flow is counterbalanced by the exactly same reverse flow. Okay. So in this case, in this junction, the holes are diffusing from P side to N side, as is clear from this picture. But that is exactly countered by hole drift from N side to P side. So P to N hole is being countered exactly by drift of holes from N to P. And similarly, the electron diffusion from N to P side is exactly being countered by electron drift from P to N side. And that's how this equilibrium is maintained. We also had a look at the band diagram of the diode, which is, I would say, uh, the importance of the band diagram cannot be exaggerated. Actually, it's extremely important notion, idea, especially in semiconductor physics. And in the band diagram, typically we have the band edges, bottom of the conduction band, top of the valence band, and apart from the band edges, we have the Fermi level. And in equilibrium, the Fermi level across the entire device is constant. And there is an important point here, actually, that I guess we did not discuss last time. That the number of carriers in a material are governed by the Fermi level in that material. So if the Fermi level is, so we saw last time that if the Fermi level is closer to the conduction band edge, then electrons will be more, and if it is closer to the valence band edge, then the holes will be more. Okay. So like if we take the case of n-type material, let's say only this side, the distance between Fermi level and ECN will govern the number of electrons, the majority carriers. So the majority carriers will depend on the distance between EFN and ECN. Closer they are, more are the majority carriers. Okay, and the distance between EFN and EVN, it governs the number of holes, the minority carriers. So if EFN is far away from EVN, which means it is closer to ECN, in that case, number of holes will be very less. So in a way, the number of majority carriers and number of minority carriers are related to each other. Do you see that that relationship? That if one is more, the other will be less, because if the majority carriers are more, EFN will be closer to ECN and it will be farther away from EVN, and the other, which means the minority carriers will be small in number. Yes, do you have a question or something?
Sir, can you please switch on the pointer?
Okay, yeah, sorry. So is this not visible? This arrow is not visible to you?
No, sir.
To none of you?
No, sir.
Oh, sorry. I thought that it should be visible there. Is this visible now? The pointer is visible to you?
Yes, sir.
Yes,
Okay,
sir.
okay. Yeah. Thanks for pointing this out. So let me quickly repeat what I said to you, that the proximity between EFN and ECN, the Fermi level and conduction band minima, that tells us about the number of electrons in a system. So if EFN is closer to ECN, which means that in n-type material, number of electrons will be more. And the distance between EFN and EVN, or EF and EV, it governs the number of holes. So if the electrons in the n-type material are majority carriers, and holes in n-type material are minority carriers, right? So if the number of electrons is more, there are a lot of electrons, it means that this EFN will be closer to EC. All right, and which also means that this EFN will be farther away from EVN. So if electrons are more, holes will be less. And if EFN is slightly far away from ECN, number of electrons will be less and number of holes will be slightly more. So in a semiconductor material, in any semiconductor material, either be it p-type or n-type or any semiconductor material, the minority carrier concentration and the majority carrier concentration are closely related to each other. If the majority carriers is more in a material, let's say if in this n-type material number of electrons is more, number of holes will be less, minority carriers will be less, and which is easily understandable from the band diagram. Because if we just look at the band diagram of the n-type material, then we can deduce that. All right, is this point clear or not?
Yes, sir.
And in the
Sir,
as
the last
yeah.
because my mic was disconnected.
Yeah, so what I said is that one thing that you need to keep in mind is that the number of majority carriers and number of minority carriers, they are closely related to each other. If the majority carriers are more in a system, in a semiconductor, the minority carriers will be less. And vice versa. If the minority carriers are more, majority carriers will be less.
Sir,
Yes.
what do you mean by majority carriers? I mean that in N-type materials, electrons are majority, while in P-type, holes are majority carriers.
No, you are right. And if you are not aware of that, yeah, you should ask actually this question as well. So in N-type material, uh, we have the doping of, let's say, arsenic or phosphorus or antimony or any such doping in which there is an excess electron, right? So once this doping is done, once the material has become N-type, it means that the dopant atoms have an extra electron which is now free to move in the lattice. So by putting dopant atoms in a semiconductor, we have put, in a way, we have introduced new electrons in the system. And this, the electrons in this system are they become the majority carriers because now we have a lot of electrons equal to the number of dopant atoms. So in N-type material, electrons become majority carriers and holes become minority carriers. Similarly, in P-type material, electrons become minority carriers and holes become majority carriers. Minority majority means more or less. So in N-type material, there are more number of electrons and less number of holes. Similarly, vice versa is true in P-type material. Number of electrons is less and number of holes is more. Okay. Is this clear now?
Sir, you are saying that majority carriers are more than minority are less, and saying na, sir.
Yes, exactly. So if uh, so, what I mean by more majority carriers is that if this doping is high in this material, let's say, so it means that more number of electrons will be there in this. It also means that the number of holes will be very less. So if the majority carriers are more in a semiconductor, in a doped semiconductor, the minority carriers will be less. So they are inversely related to each other. The concentration of majority and minority carriers is inversely related to each other. That's what I'm saying. And that's also clear from this diagram, this band diagram. All right, do you have any concern about this argument?
Sir, if the Fermi level is closer to ECN, then electrons are more in N-type and holes are less in P-type, no, sir. P-types are
No,
majority carriers.
No. So what I'm saying, yeah, I'm not going to the p-type right now. What I'm saying is, if the Fermi level is closer to ECN, electrons will be more in n-type and holes will be less in n-type. In the same material, okay?
Okay.
The minority and majority carriers are inversely related to each other in any semiconductor material. And in this junction region, as you can see, this Fermi level is, if we see the distance between Fermi level and conduction band and Fermi level and valence band, it is almost equidistant at the middle, which means that now both electrons and holes are less actually. So that's why this region is known as the depletion region. So that is essentially the picture here. And there are two type of carrier transport that is happening. One is the diffusion of carriers and second is the drift of carriers. The diffusion of carriers is because of the difference in concentration of carriers. So on p-type we have more holes, on n-type we have less holes, so holes will go from p to n. Similarly, n-type, n side we have more electrons, p side we have less electrons, electrons will go from n to p. So this is known as diffusion, and drift arises because of the depletion region, because in the depletion region there is now an electric field profile in the system, and this profile actually this introduces an electric field in the depletion region, and that will push electrons and holes from p side to n side and holes from n side to p side. And as you can see, the direction of diffusion and drift for the same carrier is reverse. So the direction of hole diffusion and the direction of hole drift is in the opposite direction. Similarly, for electrons and hole, electron diffusion and electron drift, the direction is reverse. Okay, so this is what we have seen, and apart from that, I also mentioned that this voltage that is directly proportional to the doping of both sides of junctions. So this V naught is the inbuilt potential at the junction, or it is also the barrier that is created because of combining two different kind of semiconductor materials. And it is, if the doping is more, it will be more, and the depletion width is dependent on the voltage, also on the doping. And if we just see the depletion width in terms of doping, it has a slightly complicated kind of relationship. It is not, we cannot say that it is directly proportional to the doping or inversely proportional to the doping, but there is a general thumb rule that
Sir, what
if
if
we are
Na
combined,
ND?
yes, Na is the doping on p side, acceptor doping, and Nd is the donor doping. So donor doping is on the n side and Na acceptor doping is on the p side. Okay, epsilon is the dielectric constant of the silicon. K is the Boltzmann constant, T is the temperature, Q is electron fundamental charge of electron and unit charge, and Ni is the intrinsic carrier concentration. It is the number of electrons and holes when there is no doping. All right. We did not do the derivation because this derivation is out of the scope. It needs more discussion, more number of classes, and you will do this in your second year. So this is what we had basically. One thing that I would like to highlight here is that if we try to measure voltage across any device or across any conductor, any semiconductor, if we put any electronic equipment, be it potentiometer, be it voltmeter or anything, it measures the difference in the Fermi level on both sides actually. Just keep this in your mind actually. That any measurement device, it measures the difference in the Fermi level across the device.
Sir, why is this so?
And yeah, that's a good question, and that question actually requires understanding of the Fermi level. But let me qualitatively tell you that the Fermi level governs the carrier profile, carrier concentration. So it means that if there is a gradient in the Fermi level, the carriers will try to move in a certain direction, move in a specific direction. Is this sort of clear? Is this does it make any sense?
Can you please repeat the statement, please?
So what I'm saying is that if the Fermi level is uniform across a device, it means that that now carriers are settled in this device. Carriers are in equilibrium in the device. So they will, carriers means electrons and holes, any kind of carriers, they are in equilibrium. So they will not have a net motion inside the material. But if the Fermi level is different on different, so for example, on this side we have a different Fermi level and on this side we have different Fermi level. In that case, carriers will have a propensity to move inside the device. And that essentially is the actual potential energy difference, because when the Fermi level is constant, it means that uh, that that electrons or carriers are at the same potential energy. They do not have any difference in the potential energy. But if the Fermi level is different, that is essentially a difference in the potential energy of the carriers, and that is what gives rise to the potential or voltage across the device. So although there might be a contact potential here at the junction, but across the device, since the Fermi level is uniform, there will not be any potential drop across the device, or it is not externally measurable, it is just internal electric field uh, profile that is giving rise to this junction potential in the device. Is this sort of clear? Does this make sense to you? I know this is not a very rigorous way of dealing with the Fermi level and related concepts.
You gave a question to us that when we can measure the. So
Yes, exactly. Yeah, Ayush, you are not properly audible. Hello?
hello.
Yeah, you are not properly audible. Actually. Can you please repeat your question?
So that we can't measure the voltage of the device. When
Yes, yeah, I'm answering that question from a different point of view here. Yeah, some of you answered that question that day itself, and that was right answer. And there are multiple ways of approaching the answer to that question. In some texts, it is actually they say that, and that's also all right. That when we put any measurement device, that will create new contacts with the junction. So, for example, any measurement device, it will not be. Do you see the slides on your screen or not?
No, sir.
No, sir.
No, sir.
no,
Just a moment. Is it visible now?
Yes, sir.
Yes, sir.
Yeah. So so for example, if we put any measurement device across the junction, so this measurement device will be just of one type of material. It will not be P type on one side and type on another side. It will either be a conductor, it will be a wire essentially. All right. So this device will create actually uh, new contacts here on the sides. And these new contacts will have new contact potentials, and essentially the net potential drop will be zero across the entire connection, across this entire. Is this argument, does this make any sense?
Sir, why they will make net potential difference 0?
what does new contact mean here?
Sorry, can you, so I don't know if the problem is on my side or your side. There seems to be some connection problem.
So am I audible now?
Yes, you are audible. Yeah.
what does the here?
What does?
I just
Sorry, I'm not. Still, I cannot hear anything.
Sir, he can type in chat.
Yeah, can you please repeat? Dikshant, can you repeat his question? And that way it would.
Sir, I also didn't understand his question. I was saying that he can type in the chat what he's asking.
Yes, yeah, that would be good.
Sir, I was asking that why the contact potential will be such that the net potential will then become zero.
So, yeah, the thing is that if you put any material in contact with a p-type semiconductor, if you put let's say a metal in contact with a p-type material, it will make a junction. Only the same p-type material, the same doping p-type material will not make a junction, a depletion region at the junction. Any other type of material will make a depletion region at the junction. Be either it be a n-type material or it be a metal or any other kind of. Okay. So in a potentiometer or in any voltage measuring device, we have connections, we have wires. Okay. And generally we have same kind of things, same kind of wires. Same kind means that they can be, both wires are either metallic, both wires are either semiconducting material or anything. Generally they are metallic. So if we put a metal in contact with p-type semiconductor on the left side, and if we put a metal on in contact with n-type semiconductor on right side, on both sides as well, we will have small junctions, the depletion regions on the junctions. And the net potential drop across these three junctions will be zero. So that's another argument. But at the core of it, from the thermodynamics of the carriers, the reason is that the Fermi level is constant throughout the device. So that's why any external voltage cannot be visible across this PN junction. That is more fundamental physics point of view. From an instrumentation point of view, the answer is that the contact potential will neutralize this depletion region inbuilt potential.
So why the potential difference across the three depletion regions becomes zero?
Yeah, on one side it might be a positive value, on another side it might be a negative value. So in total it becomes zero. And as I said, it is the reason for that is that the Fermi level is constant throughout this junction. So that is a consequence of that.
Sir,
Yeah.
sir, you explained that difference in Fermi level develops the potential difference. But how do we know that the difference will be equal to the difference in Fermi levels? The potential difference will be equal to difference in Fermi level.
How do we know means that is actually so if you want to calculate the potential across any device from fundamental physics of that device. Fundamental physics means from the basic, from first principles, from the basics of that. Then we need to calculate the Fermi level across the device. And once we make a calculation of the Fermi level across the device, and if we see any change in the Fermi level, that will be equal to the, or that will tell us about the difference in the potential energy, and that will translate in a potential drop or a voltage drop across the device. And that's also the answer to the previous question, that it is since the Fermi level is constant, and that's why any new any connection will not measure, or any potentiometer or any voltage measuring device cannot measure any voltage across the device, because the electron's potential energy is in a way constant throughout the device. So there is no inherent uh, potential across the entire device. Although at the junctions, electrons might feel electric field, but that field is is increasing on one side and maybe decreasing on other side.
So,
Yes.
sir, in a normal circuit where there's no semiconductor, there's a load and conducting wires. In that, voltmeter measures the potential difference. Is there a difference in Fermi level in that circuit?
Yes, exactly. Yeah, that's always there. So generally in metals, so generally those circuits are metallic circuits, right? Because even most of the resistors are metallic, and most of the wires that we use in circuits are metallic. So everything is metallic in that. And generally metals are simple because in metals, we do not have conduction band and valence band, the notion of conduction and valence band. We just have the notion of Fermi levels. And even there, if there is a voltage, if there is a current flowing through a resistor, let's say, it means that it will have a difference in the Fermi levels. And that difference is essentially reflected in the reading of the voltmeter or any device that is measuring. Even in this case, even in a PN junction, if we make a current flow through the junction, if we sort of somehow maintain a current, that will change the Fermi level, and that will be reflected in the in a voltmeter reading finally. So I must say that just keep this in your mind. Actually, just don't. Uh, uh, I'm pretty sure that all these things cannot be discussed here because this notion of Fermi levels cannot be fully discussed here. Just keep this in mind that ultimately, at the most fundamental level, it is the Fermi level that governs the transport of charge carriers. Okay, and maybe in your further readings or maybe in our further discussions, these things will be more clear once this idea of Fermi level is discussed in greater detail. Okay. Yeah, there was some more questions. There were some more questions, I guess.
Sir, if Fermi level is constant, then how it can be changed?
It can be changed by applying a battery, or it can be uh, by putting more number of carriers on one side. If we, so for example, if by any mechanism, or if we create more carriers on P side, just P side, it will change the Fermi level. You would ask me an example actually. So the example is that if we shine light on this PN junction just on the P side, on one side, let's say we have covered the N side and we shine light on P side, it will create carriers in P side and it will change the Fermi level actually. And if we shine light on N side, similarly, it might change the Fermi level. Or the other way is if we connect a battery, it might change. Or if we put this diode in a circuit where uh, a battery, resistor, or other electronic components are there, then also it can change. Okay. I guess we have had quite a lot of discussion on this this thing because it is because we are running short of time. There are limited number of classes. But if there is any pressing question, please ask. Or are things all more or less clear? I won't say everything is damn clear, but are things more or less clear?
So they're more or less clear.
Okay, yeah, good to know. Everybody?
Yes, sir.
Yes, sir. Same.
Sir, it's getting a little bit complex for me to understand things.
Yeah, actually, yeah, that was my concern as well in the beginning. So that's why I did not want to go into the discussion of band diagrams, Fermi level, because it might be too much. But ultimately, we have to understand, if we want to understand semiconductor physics or any solid state physics, this is what we need to deal with actually. So I must say that The semiconductor physics is not easy, but as such, it's a challenging field, and it's an interesting challenge. It's a worth-taking challenge. Okay, there are many new concepts, there are many new ideas, but once you get it, then it's not so difficult. The other thing is that generally this part of physics is not taught to us in our schools, in our up to our 12th classes. So up to 12th classes, generally the optics, electrostatics, electromagnetics, all those things are taught in good detail, and that's why those things are, we are quite familiar with those things. And this is a new domain of physics that we encounter, and because of many new concepts, many new uh, ideas, in the beginning it looks difficult. Okay, so don't worry about it, just keep these things in mind, that these are various things that might come in these kind of devices, or in semiconductor physics, or in condensed matter physics. This is a branch of condensed matter physics actually.
Sir, would you please suggest any reference for this, just to understand better?
Yeah, so if you have free time, then I would recommend you to read Streetman and Banerjee, Solid State Physics. Maybe I'll share the PDF with you guys, all of you guys, okay? And apart from that, there is another book by Robert Pierre, Advanced Semiconductor Fundamentals. But that's a bit advanced book. That's not for UG first year or even second year. Not recommend. So this Streetman and Banerjee is a decent book. It's a standard book, and in any case, you would need to read this book in your second year. So maybe you can begin right from here. Okay. I'll share the PDF of that book.
What is the name of second book?
Robert Pierre. So it's a French name, and the spelling of the Pierre is Pierret. Pierret. In English, it might be Pierret, but in French, it is Pierre. Robert Pierre.
Okay, sir.
I personally like Robert Pierre more, because that approaches things from more fundamentals, but that requires a bit of background. So maybe once you have gone through Streetman and Banerjee, then you can move on to Robert Pierre. Okay, so with this, let's maybe go ahead, and now I guess things are now, since things are more or less clear, when there is equilibrium, no bias, no external voltage, this is the status of the PN junction. In forward bias, the depletion region is reduced, the diffusion current becomes more, because in forward bias, and this I guess we discussed last time, in forward bias this barrier is reduced, and with the reduction of the barrier, the diffusion component of the current actually becomes quite dominating. It becomes extremely large as compared to the drift component, and that's why there is a net current in the junction in the forward bias. In the reverse bias, this barrier is further increased, and because of that, the diffusion current becomes almost zero, and the only current left is the drift current, and the drift current is actually a very small component of the current. It is in microamperes or even in nanoamperes, and that's why in reverse bias we have a very small current, very negligible current, I would say, and in forward bias we have a significant current in milliamperes, and
Sir,
that is, yeah.
so when we apply external electric field and then electron flow from N to P, will we call that drift current, or it will be only diffusion current?
Diffusion current. Electrons flow from N to P. It means that uh, that is not due to, so electrons are not flowing because of the electric field, just because of the electric field that is applied externally. Electrons are flowing from N side to P side because now this barrier is reduced and they see empty states on P side, and here those states are filled. So they can quickly jump to these states. Okay. So in forward bias, That's why this current is known as the diffusion current. Drift current will be when, because of the electromotive force, the carriers will be moved. In this case, that is not happening. Okay, so so that's why. So this is the picture here, and as I told you, that this drift current is because of the minority carriers and diffusion current is because of the majority carriers. And there is a small point here that as we discussed, that the majority carriers and minority carriers population is related to each other, because the Fermi level, if the Fermi level is close to conduction band, it means electrons will be more, holes will be less. So if one is more, another will be less. So they are sort of inversely related to each other. In the same way, the diffusion current and the drift current are also related to each other, because current is ultimately charge flowing as a function per unit time, or flow of charge. If we take a derivative of charge with respect to time, which means the flow of charge with respect to time, in time, that is the current. So the diffusion current is related to the drift current as well. And if the drift current is Is, the diffusion current will be Is exponential Vd by nVt. This is the expression for the diode current. This is an important expression. Okay. We have not derived this expression in this class. It needs it needs an understanding of more advanced concept that we did not deal in greater detail here, but it will be derived in ECN 242, which will be there next year. But please remember this expression that the diode current, when a Vd voltage is applied across the diode, the current is given by this expression. ID is equal to Is times exponential Vd by nVt minus 1.
Sir, pointer is again not visible.
I guess pointer is not there. Is it visible now?
Yes,
Yeah,
sir.
please remind me if you don't see the pointer. Yeah. So this current expression, as I said, is important, and in the forward bias, so this first on the right hand side, the first term is the diffusion current, and the second term is the drift current, and the net current is the difference between the diffusion and the drift current. Okay.
So can you please tell what is Is and N and Vt in this?
Yes, yeah, I was coming to that. Is the drift current or the minority current. So as I told you that drift current is because of the minority charge carriers. So from the N side, the drift current is of the holes, and those are the minority carriers. Similarly, on the P side, the drift current is because of the electrons, and those are the minority carriers. So this drift current is generally constant. It is almost independent of the voltage actually. And the reason for that is that even in the absence of any voltage, there is an electric field in the junction, and that electric field can sweep the minority carriers across the junction. And if we apply a voltage, this electric field will change, but it does not change the current value significantly, because current depends on electric field and mobility on the velocity of carriers. And when we join them together, it's almost this product of J is equal to sigma times E. So this product is almost constant. So this drift current or the minority current is almost constant as a function of voltage. And that is denoted by Is. Is means the saturation current. It is actually the reverse saturation current. When we have a reverse bias, the diffusion current becomes almost zero, and the only current that is left is the minority carrier current, and that is the reverse saturation current. It is denoted by IS. VD is the voltage applied across the diode. If VD is positive, it is the forward bias. If VD is negative, it is reverse bias. In forward bias, the positive terminal of the battery is connected to the P side and the negative terminal is connected to the N side of the junction. In reverse bias, the positive terminal is connected to the N side and negative terminal is connected to the P side, opposite to the forward bias essentially. Okay, and as I told you that this diffusion current is related to the drift current as well. So the diffusion component of the current is given as drift current times this exponential, IS times e to the power VD by NVT. Yes, there is a question, I guess.
Sir, in reverse bias, the depletion region is thickening. So, sir, how the ions are moving in that?
How the ions or electrons holes?
Sir, acceptor ion and donor ions are moving.
No, acceptor and donors, they do not move. They cannot move. They are the static charges.
So, sir, how the
Why
depletion
do you?
region is getting?
Carriers.
Okay, yeah. So your question is, why is the depletion region getting large in this case?
Yes, sir.
Yeah, this is because now these acceptor and donor atoms are uncovered. More number of, so if we apply, for example, a positive voltage on N side and negative voltage on P side, positive voltage means it will attract electrons to this terminal. So more number of electrons in the N material will be attracted to this side. Similarly, on P side, holes will be attracted to this terminal. So these electrons will leave donor atoms uncovered, sort of as shown in this picture, and that will increase the depletion region width. And vice versa is true in the case of forward bias.
Okay, sir.
Is it somehow is it more or less clear now?
Yes, sir.
So yeah, I'll finish with this IV characteristics.
Excuse me,
Yes.
Sir, those positive ions were formed because they lose the extra electron they were having, these donor atoms. So if we are like applying forward biasing to the diode, then how can they gain the electrons so that the depletion region becomes less wide or become
Yeah,
thin?
it's not that they are gaining it. The electrons are not participating in the bonds because these positive ions can only form 4 bonds, but they had 5 electrons. But
Yes, sir.
now the electron cloud is there around these atoms, which means that in effectively they will be neutralized. So if there are free electrons around these static ions, a cloud of electrons is there, and that is there because of the forward bias, because in the forward bias we apply a negative voltage which pushes electrons to this side. So it basically pushes electron cloud to to these atoms, and so effectively they become neutralized,
Okay,
and
sir.
the depletion region
Sir,
is reduced. And yes.
sir,
Yeah,
if
please.
in forward bias the electrons are pushed towards the depletion region, then why the positive ions are not left uncovered at the terminal?
No, these electrons are getting supplied from the battery. They are not being supplied just from the semiconductor material.
Okay, sir.
So these excess electrons are not coming from this semiconductor. They are coming from the battery terminal.
And sir, what is VT in that
Okay.
expression?
Yes, exactly. Yeah, I'm coming to that. There are two parameters that are left. One is N and second is VT. VT is the thermal voltage and it's a constant. So VT is essentially this KT by Q. K is the Boltzmann constant, T is the temperature, and Q is the electron charge. So quickly, can you do this calculation, or maybe just do this calculation on your own? What is the value of VT at room temperature? As you can see that VT is only dependent on temperature. The rest of two parameters are constants. So VT is also known as the thermal voltage, and it is given by KT by Q. And I would recommend all of you to do this calculation. It's a small sort of calculation. What is VT at room temperature? Okay. I hope you know the Boltzmann constant and the electron charge. So that calculation should not be difficult. And N here, so this VT is clear now?
Yes, sir.
N is the ideality factor of the diode. Ideality means how ideal the diode is. Okay. So as I mentioned right in the beginning that generally the diodes that we manufacture, they are far from this kind of diodes because during manufacturing we cannot make sharp junctions. That's extremely difficult. That's extremely unlikely, I would say. Okay, and there might be some defects at the junction as well. There might be dangling bonds. There might be mismatch between the bonds, and because of those non-idealities, this current is affected, and that is accounted for by this parameter N. Okay, so now I guess all the parameters are clear. So this is the diode equation, and if we look very closely in this equation, prima facie this looks like a simple equation. It's just as simple as it, but it contains a lot of physics actually, as you might have already sensed. The equation has a thermal voltage in it, which means that somehow it is dependent on temperature. It depends on non-idealities,
Sir,
defects. Yeah.
sir, at steady state, ID will be 0
Yeah.
because I majority.
At steady state.
At
Sorry,
steady,
at steady state.
I majority will be equal to I drift.
Yes, not at steady state, at equilibrium. Equilibrium, this ID diode current will be 0.
Okay.
Sir, what is the typical range of N?
Steady state can be there in forward bus. Yes, so N is generally 1, 2, or sometimes it is, so in some cases it is less than 1 as well, 0.6. But it typically goes from 0.6 to 2, not more than 2.
Okay, sir.
And generally, if N is not given, then just take it 1. Okay, in any question, if the N value of N is not given, you can take it 1. And if it is explicitly mentioned, then you need to take that particular.
And sir, what is the
so
range
what
of
I was
VD?
VD can be, so this positive VD can be from 0 to typically 0.7, 0.8. Because once VD in silicon diodes, if VD reaches 0.7, then this exponential factor becomes extremely large. Because this VT, although I told you to calculate VT, but VT is 26 millivolt at room temperature. And if N is 1, and if VD is 0.7, let's say, it means 700 millivolt. So the factor will be 700 by 26. So this becomes extremely large factor, and this exponential becomes. So even at 0.6 or 0.7 volts, this current becomes extremely large, and VD cannot be increased beyond that value, because even a small change in VD will result in huge change in current, and that will essentially the it means that the battery may not be able to supply that much current, actually. So it cannot be increased further. Although on the negative side, the VD can go to large negative values, -4, -5, or even -20, 30. Okay.
So
And
this
is the
equation,
ideal and yeah, sorry.
so sir, this equation gives
Sorry, yeah,
that
you were saying.
graph of diode, which we see IV graph.
Yeah, so this is this graph actually comes from this equation. You might have seen this graph at many places, I guess. This is the IV characteristics of the diode. So that is essentially the relationship between ID and VD. And so what I was trying to point out is that although this equation might look very simple or just like an exponential equation, it contains many different actually physical processes going on. It contains the drift, it contains diffusion, it contains it is dependent on temperature, it is depends on device geometry, construction, external parameter VD. So it contains a lot of physics actually. And uh, understanding this equation, deriving this equation or a derivation is also very important to properly understand the semiconductor device physics. Okay. So, and I must tell you that if you understand the junction physics properly, how a simple PN junction works, then understanding all other electronic devices, it's easy actually. Understanding a BJT or understanding a MOSFET becomes very easy. Okay, so it's like a one-time investment to understand a PN junction, and once you properly, thoroughly understand this, the semiconductor device physics actually uh, becomes tractable. It becomes easy. Okay. So I think you guys might be tired by now because you might had classes since morning. Although there are a lot of things to discuss, but let me not take more time. So are you free tomorrow for an extra class? Because we missed 2 classes, so I want to make up for those 2 classes. I'll maybe talk to your CR and she should be able to tell you that. Okay, but we might have an extra class tomorrow, so that we are not very we are not lagging in our curriculum.
Okay.
Okay.
Sir.
So can you
Any
please tell
final
us the empty syllabus?
MT syllabus will be whatever will be discussed till MT, and that is essentially the semiconductor device physics, circuits, basics of circuits. So next few classes will also be there. So what is uh, discussed just before MT will be there in MT. Okay.
Sir, what will be the pattern?
So the pattern I would say is might be, although I have not thought about the question paper yet, but whatever we discuss in the class, that is, questions will be based on that. Okay, so if you understand things in the class, you understand the discussions or understand the slides, then you should be able to answer almost all the
It's
questions.
subjective or MCQ.
So I think it would be subjective. Actually MCQs in online mode are not reliable, so it would be subjective. Okay, but I'll decide that uh, maybe in the first week, after first week of January, just before the MT. Okay. Anything
Sir,
else?
sir, I have
Yeah.
a question. Sir, how is ideality factor determined?
Yes, ideality factor actually, uh, as I told you, that it depends on many things. One is it depends on how perfect the junction is. And so in diode equation, while deriving the diode equation, if we take those imperfections into account, if we take recombinations because of the defects into account, that essentially introduces a factor in the exponential. And that's where this n value comes from. So nowadays, these n value is nowadays standardized, because nowadays a lot of experiments have already been done, and we typically know what would be the value of n for a typical junction. For example, if a junction has non-uniform doping on both sides, it is not a sharp junction. In that case, we can say that this ideality factor will be between 1 to 1.5 or something like that. And if there are a lot of surface defects, it would be around 0.6 to 0.8 or things like that. Okay. So one way is to account for those non-idealities in derivation. Second is we make a diode, we may measure the current across the diode, and then we fit this diode equation to that current plot that we obtain in experiments. And from that fitting, we generally can deduce the n value as well. Okay.
Excuse me, sir.
In ECN 242, just to sort of make it clear here, in ECN 242, which is your second year course, you will have a lab, and most likely I would be taking that lab. In that lab, you will measure the diode current, and you will be fitting this diode equation in that current, and then you can you will do it yourself.
Okay, sir. Thank you, sir.
Yeah, Dekshant, you had a question.
Sir, how can I reach you to discuss about the project? You said like we can discuss separately.
Yeah, you can send me a WhatsApp. I'll reply you whenever I'm free.
Sir, can you share your number?
Yes, I guess I shared my number already. My number with you. I'll share my number over the email to all of you. Okay.
Okay, sir.
Okay. If there is no more question, then maybe we can close.
Thank you, sir.
Yeah,
Thank you,
alright.
sir.
Yeah, thank you.
Thank you, sir.
Thank you, sir.
Bye bye.
Thank you, sir.